The next speaker in the morning session is Tim Horbury of Imperial College London, who will review the solar wind for you. And the solar wind does have enough resolution.
Yeah, it does. Absolutely. Thanks, Alex. And first of all, thanks for the organisers for the invitation to be here. Oh yeah, the second thing I should say is, in your programme, this is not my abstract, as I hope is quite obvious from reading it. I'm Tim Horbury. This is the abstract of Will Hornsby. Okay. No, this is worse than that. I actually. Yes, that's right. He's got a very interesting poster. I would encourage you to go and have a look at it. But it's actually worse than that, because I think this is going to run and run. You know, this is Will has not been long in the field, and actually I vivored him not very long ago. So I really should have thought this through and failed him, because I think this is going to be a running theme for the rest of my career. So, right. Okay, so what I'm going to try and do this morning is give you a very broad brush, relatively simple introduction to the solar wind and the kind of things that we know about turbulence in the solar wind on ion scales and on fluid scales, predominantly fluid scales actually. So it's not going to be very detailed, and the people that know about what I say are probably going to huff and puff and think that I could have said it better, and I apologize in advance. But I'm just going to try and give an introduction, particularly for the tokamak people and the simulation people, to give a flavor for what it is that we know, what we can measure, and indeed what we don't know. Okay, so I'll start off talking a little bit about what the solar wind is like and what we can measure in it, and then some of what we know about the basics of the fluctuations, what they're like. And I'll talk in detail about the MHD scale cascade, and then about the ion scale cascade in a little bit less detail, and a tiny amount about kinetics. And many of these things are going to be talked about in more detail by speakers later on in the week, so I'll just touch on them as I go along. Okay, so let's start in the beginning. What's the solar wind? Well, it's a mostly collisionless magnetized plasma. It comes from the sun, of course, and it's very hot, and in particular, it's extremely variable and structured on every scale you can measure. I don't know how well you can see this movie. But this is a movie taken from a camera called the heliospheric imager on one of the NASA stereo spacecraft. There's dates and times coming down here, so you can see this is greatly speeded up. The general background you can see here are stars. This is the Milky Way. Okay, so this is a very, very, very deep camera. It's a very sensitive camera. The sun, as I hope is obvious, is off to the right, and this stuff streaming past here is the solar wind. So you can see it's incredibly structured. There's stuff going on all the time. This is very large-scale stuff. There are occasionally individual events that come off, things like coronal mass ejections. One should come off. There you go, like that. There's all this structure going on all the time. Okay. The turbulence that I'm going to be talking about is completely invisible on this scale. It's very, very small compared to this. But all the time, we have to keep in mind the fact that we're in this very structured, variable medium. Okay. So we're not in control of any of that, and you have to remember the context all the time of what's happening. Okay, so just a few parameters to give you an idea. It's mostly protons. There's a few percent alpha particles, so doubly ionized helium that's come from the sun as well. There's a small fraction of heavy ions, things like neon and carbon and oxygen, which are mostly but not entirely ionized. And of course, there's an equivalent number of electrons. So there's things there about temperatures. It's doing a few hundred kilometers a second. The alphane speed is the order of 40 or so kilometers a second, a few tens. So it's very super alphanic. The Debye length is the order 10 meters or so. The mean free path, although this is rather variable, at 1 astronomical unit, and we're at 1 astronomical unit from the sun, the mean free path is about an astronomical unit, so it's pretty collisionless. So the gyro radius is of the order of 100 kilometers or so, inertial length. The magnetic field is a few nanotesla, so we're a bit down on a tokamak. And the beta is of order 1, and I'll come back to that later on. Okay, so what is it to make a measurement? What does it mean to make a measurement in the solar wind? Spacecraft, and I've produced some pictures here. These are actually the 4 cluster spacecraft, European cluster spacecraft, and I'll come back to cluster data later on. These 4 fly in formation together around the Earth. These are funded by the European Space Agency. And ESA, in their press photos, put in 2 standard-sized people, so you can look at scale. So you see these spacecraft they're a few tons and they're a few meters across. Okay, so these are typical kind of spacecraft. So generally speaking, given the fact that the gyro radius is 100 kilometers, so this is pretty well a test particle. However, the fields in particular are very low, and so we have problems with contamination of magnetic fields from spacecraft systems electric fields with wake effects and this kind of thing. So there are instrumental issues, but in practice, actually, the measurements that we make are really pretty good, as you'll see. So we measure the magnetic field, electric fields, bulk ion properties like velocities and densities and temperature, so on are pretty straightforward. For the electrons, they're slightly harder, but not by no means impossible. We can measure full distribution functions in 3D as well. So those kind of things are kind of a done deal. And we can measure energetic particles as well. Okay, so we don't just have measurements near the Earth. In fact, spacecraft have explored most of the solar system. However, most of those spacecrafts have not been designed really for plasma physics. Most of the measurements we have around the solar system are from spacecraft which were designed to explore planets and this kind of thing, like the Voyagers and these kind of things. So as a result, they do have plasma physics packages, but they're not actually particularly great. And so there is always a continual problem. If you took best of class of every magnetic field, electric field, plasma, and so on measurement, and put them all together on one spacecraft, you'd have an unrivaled set of measurements for doing plasma physics in space, but nobody's ever actually done that yet. So we have bits and pieces from various spacecraft. One other thing that I show you from this picture, these are data taken from the Ulysses spacecraft, which is the only one that's gone over the poles of the sun. And so what's plotted here is from the center outwards is the speed of the solar wind as a function of where the spacecraft was with latitude. And you can see that there are regions where the solar wind is very fast and actually relatively steady, and regions where it's much slower and more variable. And we're down here. One of the big things to remember about the large-scale structure of the solar system as you move around within it is that the properties of the solar wind change, and the biggest one of those is the distinction between this high-speed, steady, well-behaved wind and the low-speed, crufty, nasty kind of solar wind. Okay? So there's this lovely smooth stuff, which is actually coming out of magnetically open regions on the sun, and there's slow, scruffy kind of wind as well, which is much more variable and perhaps more complicated to understand. Okay, just to give you an idea about what it looks like, what the kind of measurements you get, this is 30 days of data taken near one astronomical unit, near the Earth. It was actually taken in 1976, but the data don't go off. I thought I might as well show some old data. I was 5. So the set of parameters that are shown here, if we start at the bottom, this is the solar wind speed in kilometers a second. So you see this is going between about 400, 500, 600 kilometers a second, up and down, with the time scales of a few days. And that time scale is actually because the sun is rotating underneath you and is bringing past you streams which are going more quickly or more slowly. A fast stream hits a slow stream and generates a compression. This is the proton number density. You see you get these peaks, and that's because of dynamics of the fast stream hitting a slow stream. Similarly, the temperature can go up. You can get shocks, those kind of things. The magnetic field magnitude is above that, so you can see that's kind of going up when there's compression, but equally there's a lot of general variation. And the two at the top are the angles of the magnetic field, a kind of azimuth and a poloidal angle, and you can see they're all over the place. And if I just, this is 3 days here, actually within a high-speed stream. This is the magnetic field magnitude, which is relatively speaking fairly constant. All of these dips are actually things like mirror modes and so on, but generally speaking, things are pretty constant. But you see the angles are all over the place, and this is the turbulence. Okay? So this is in a high-speed stream where you can get several days at the same time of relatively steady, statistically stationary data that we can actually analyze. But all the time, we have to bear in mind that we're within this complicated structured medium.
Why does it drop out at 175 days?
Okay, that's the other thing about spacecraft. They'll be like the antenna was not pointing the right way, or on the ground as well. Well, I know with Ulysses, we used to have nasty problems. One of the dishes is in Spain, and whenever it rained, they couldn't get a good signal. You spend $500 million on a spacecraft, and then it rains. And it rains in Spain, and it's on the plane, though. This is it actually is on the plane. There was a classic day as well in the Ulysses. I mean, this is from years ago now. The Ulysses operations file. We missed a day of data, and it turned out to be because the antenna in Australia couldn't be pointed the right way because school children were throwing stones at it. I say shoot the school children. Oh no, they're recording it. No, they don't shoot the school. I think you spend that much money on a spacecraft and you don't put a fence around it big enough around the antenna to anyway. Whatever. Okay, so there is a practical thing here that life gets in the way. So we don't have always these lovely smooth continuous data sets you might hope for. Certainly data quality in terms of return is an issue as well. That's got better over the years. Okay, so that's the kind of wiggles and things that we see. What do they mean? What does that mean in terms of what's going on in the plasma? So as we've seen, the flow is very fast compared to the wave speeds. And as a result, it's super aphanic, it's super everything, it's super fast and slow mode as well. So we can use Taylor's hypothesis to convert the time series that we get into a spatial sample. So in other words, the stuff is going over us much faster than it gets a chance to change. So our time series is really just a spatial sample through the flow. So we can convert a spacecraft frequency f into a flow parallel wave number k. So that's nice, and that's basically almost always valid in the solar wind, at least on MHD scales. Things get perhaps slightly more complicated on kinetic scales, and there are other places in the solar system where that doesn't really work, but in the solar wind it's pretty good. So what that means then is, if this is my low quality sketch of a set of magnetic field lines, and our spacecraft is over here on the left, the flow is of the plasma relative to the spacecraft is right to left. So in the plasma frame, all we get is the measurements along a straight line cut through the plasma. And that's fine unless you start becoming interested in anisotropy, which is really what my talk is going to be about. And the trouble with that is, therefore, we only get measurements along one line. So what is happening in this direction? I have no idea at all, because I can't measure across it. I can only measure in this direction, and that makes life hard. OK, so things we know. Well, first of all, we know that there is an extended MHD scale inertial range in the plasma. So this is just a power spectrum of the trace of the magnetic field components. And you can see there's a regime here where the power spectrum is 5/3 for 2 or 3 orders of magnitude. The gyroscale is basically near the bottom of this plot down here. I'll show you higher frequency stuff later. So we have an inertial range there, which is 2 or 3 orders across. So actually not that much different from the tokamak, I guess, in terms of scale range. The field magnitude is an order of magnitude or so less, so it's not that compressive. The other thing that we know is that there is actually an active turbulent cascade going on. So if I go back to this plot, this could just be stuff coming from the sun that's just frozen into the plasma that isn't actually active. But we know that turbulent cascade is active. We know that in a number of ways, but one of them is in this plot here. And this is the same kind of power spectrum, but taken at 3 different distances from the sun. And they're the numbers down the left-hand side. So the 0.9 AU is basically near Earth orbit, a little bit closer to the sun at 0.7, and then 0.3 astronomical units is as close as we've ever got to the sun. That's a little bit closer than Mercury. What you can see is, as you go further from the sun, the amplitude drops. That's just basically a big kind of adiabatic expansion. But also there's this break point between, this turbulent inertial range here on the right-hand side. The 1 over f, there's an f to the -1 stuff at low frequencies, okay? And that really is stuff that's come off the sun. That's basically alphane waves that are just carried out by the solar wind. And you can see that the frequency of the transition between the two, as you go further from the sun, is moving to lower frequencies. You can't do that unless you transfer energy from one scale to another. And that's telling you that actually there is an active energy transfer from these scales to progressively smaller scales as you go further from the sun. In other words, there's some kind of cascade going on. And you can show that in various other ways as well, through things like ion heating rates and the rate at which the power drops with distance from the sun. So we know there is an active turbulent cascade ongoing in the solar wind. OK, just quickly, because I know people are interested in densities and tokamaks, there is also a broadband density spectrum. I'll come back to that on ion scales later on. But we do see a broadband spectrum. There is evidence for some kind of break at the ion gyroscale as well. And there is some suggestion that it behaves as a passive scalar on MHD scales, but that's by no means a done deal at this point. OK, so I told you that there's a 5/3 spectral index in the MHD scales in the inertial range. In fact, life is more complicated than that. There is evidence that, there is a pointer. There is evidence that, in fact, the scaling is 5/3 for the magnetic field, but it might actually be 3/2 for the velocity. So this was first shown by John Podesta, and I'll show you a slightly different plot here. This is a histogram of, in fact, this is the scaling of the second order structure function. So take this number and add 1 to it to get the spectral index scaling. So if you look at the histogram for, this is the magnetic field, this peaks at a value here of about 1/3. So in other words, that's 5/3. So that's the familiar Kolmogorov scaling index for turbulence for the magnetic field. This is for the velocity, and here the histogram peaks at around about 1/2. So that's the 3/2 scaling for the velocity. So this seems to actually be fairly robust. If you go and do this, at least in high-speed solar wind streams near the Earth, this seems to be what you get. And this is a bit of a conundrum. So as I'm sure many of you are aware, there are theories for MHD turbulence that involve predictions of 5/3, that some others, for example, Boldyrev predicts 3/2, and I know 3/2 comes out of many simulations. So this seems like a conundrum of the highest order. I don't think this is actually that big a conundrum, but it certainly isn't resolved in the literature at this point.
What are the other color traces?
I can't remember.
Green is slow, red is fast.
Oh, sorry. Yeah. Okay. Thanks. Yeah. Sorry. So this is fast wind versus slow wind. Yeah.
And this is the trace of the.
This is the trace. That's right.
Why do you think it's that much of a conundrum?
Oh, I kind of think I know why it is. I think it's quite obvious actually, but sorry, I shouldn't. We're going to talk about the other three. Sorry. No, I think it's okay. Related to alphanicity, I think it's. I'll come back in a moment to the fact that a lot of the turbulence is imbalanced. So there's more. There's a dominant sense of alphanicity in one sense or another, and I think that leads to a different spectral index in B and B. I think that's pretty straightforward. Oh, here we go. So at least in high-speed solar wind streams, the solar wind is usually dominated by fluctuations which are alphanic in the sense that are propagating away from the sun in the plasma frame. So here is 24 hours of data. These are three components of the vector of the magnetic field in bold and the velocity as a thinner line. So these are the three components. There's two traces on each, converted into velocity units. And you can see that the magnetic field and the velocity follow each other really very, very closely here indeed. Okay? So that's symptomatic of alphanic fluctuations propagating anti-parallel to the magnetic field. This, I should say, is on a large scale. So remember, we're talking about the cascade here that we look at is on spacecraft scales of up to an hour or so. So really, this is the large-scale alphane waves which then are decaying to produce the cascade. So you're not really looking at the cascade here, but as we'll see, the cascade itself inherits this alphanicity. Okay, so you can have days like that, and you can also have days like this, where you see they're anti-correlated. And really, that's just a function of whether that day had an average magnetic field direction that was pointing towards or away from the sun. So the alphanic fluctuations in high-speed solar wind, where you see a dominant sense, are almost always propagating anti-sunward in the plasma frame. And that's actually quite easy to understand in terms of the way those those large-scale fluctuations are generated in the sun's corona, in the sun's hot upper atmosphere. So that's not a problem. That's fine. But basically, this is the input condition for the turbulent cascade in high-speed solar wind.
Tim, how is the velocity measured? Is that from looking at the distribution and getting the...
Yes, the peak of it. That's right. That's right. Yeah. So again, that's actually a relatively straightforward business. Yeah. So the solar wind is a cold beam. So the thermal speed is a lot lower than the Bock speed. So in fact, actually finding the peak of that distribution and moving it around is relatively straightforward. Temperature's a bit harder. The opposite is the case for electrons. So the electron thermal speed is bigger than the Bock speed. So getting the electron temperature is easier, whereas getting the electron velocity is harder.
But this velocity could include the parallel velocity, which has nothing to do with the alpha.
Yes, well, I've taken a mean off these, yeah, which is why they...
Parallel to the magnetic field.
Oh, I see. Sorry, yes, yes, that's right. No, the fluctuation includes everything here. That's right. Yeah. But they are small, typically, relative to the perpendicular. Okay, so we can look at the alphanicity using our Sasa variables. So this is just, I should have put a plot on. So I can just define variables that are things like delta V plus delta B. So this selects alphanic fluctuations in the two sensors. So this is a standard business, and this has been done for a long time. So this is pretty old data, but it's still pretty good. And what's shown here is the power spectrum of these two sensors of alphanic fluctuations. So here, if you look, this is the solar wind speed. This is relatively slow for solar wind, and you can see that there's a difference between the outward mode and the inward mode that's maybe a factor of 2. It's not particularly huge. And this is the 5/3 spectral index here. On the other hand, if I go to high-speed solar wind, you can see that this variation is actually huge. This is more than an order of magnitude. This is extremely imbalanced in the lingo. So we have a dominant outward sense here. To put this in context of the magnetic field power spectrum I showed you earlier, this is the f to the -1. This isn't really turbulence. This is just stuff coming from the sun. This is the 5/3 turbulent cascade here. And the outer scale, the edge of the turbulence, is kind of here. So from here on in is what you would call turbulence in some sense. So So you see it's being born with a very high imbalance in the fluctuations of more than an order of magnitude. So if we're going to understand solar wind turbulence, we need to understand it in an imbalanced way. And actually, I would say not a lot has been done to study imbalanced turbulence in the solar wind in recent years. Okay, so let me talk now about anisotropy. So that's a kind of broad idea about what the fluctuations look like, a power spectrum, so on. Let me talk about anisotropy, and this is anisotropy relative to the local magnetic field direction. We know there's anisotropy there. We've got lots of evidence for that. This is one example. This is 4 hours of magnetic field data. Here's the field magnitude. The two angles of the magnetic field are the solid lines here, and the little black dots are, for each time scale covered essentially by the little black dot, it's the direction in which the magnetic field vector varies least for those few minutes. It's minimum variance analysis, in fact. So each little black dot tells you the direction in which the magnetic field is varying least. And as you can see, that follows the local magnetic field direction very closely. The large variations in the field angle are due to these low frequency, large amplitude Alfvén waves that have come from the sun. That's this f to the minus 1 stuff. On top of that, there's the turbulence itself, which you can't see in this plot. It's on a smaller time scale, but the dots are picking that up, and as you can see, that follows the local magnetic field direction really very closely indeed. So the small scale turbulence rides on top of these large scale Alfvén waves. And actually that's quite convenient for us in an analysis sense, because these large scale fluctuations make the magnetic field direction sit at many different angles relative to the flow direction. And that's something that we take advantage of when we look at anisotropy. So before I go further, let me say what I mean by anisotropy. There's lots of types of anisotropy. You have to be careful what you're thinking about. One is variance anisotropy, which is really what I just told you about. The fluctuations tend to be perpendicular to the local magnetic field direction. You could talk about wave vector anisotropy, which is that at a given wave number, there might be more energy in wave vectors at one angle to the field relative to another, and as we'll see, that's true in the solar wind. There might be scaling anisotropy or spectral index anisotropy, which is that the fluctuation scale, power varies with wave number differently in different directions to the field. There can be anisotropy of energy transfer, which is that the cascade goes at a different speed in one direction to the field relative to another. We think that's true as well. And then there can be this imbalance that I talked about. So in other words, an anisotropy in the sense of the fluctuations one way or another. So anisotropy can be many things to many people. And really from now on, I'm going to be talking about these kind of ones here. These are all interrelated. So as I think is well established in MHD, generally speaking, energy transfer tends to go to higher perpendicular wave numbers in a very crude sense. So what does that mean? So here in wave vector space, if I've got parallel to the magnetic field, k parallel and k perp, generally speaking, if I put some energy in, it tends to go to higher perpendicular wave numbers. In a critical balance sense, this wouldn't be straight up, it would be at some angle like this. I'm not going to go into that in any detail. But what does that mean in terms of the structure of the magnetic field? Well, in hydrodynamics, if that's an eddy, and I'm not very good at drawing eddies, so it's a circle, then these are generally, on average isotropic, and when they fall apart, they generate isotropic eddies as well. On the other hand, in MHD, if I've got some scale along the magnetic field, which is k parallel, and some scale across, which is k perp, if I increase k perp but not k parallel, that means my daughter eddies are going to be comparably long, but they're going to be thinner across the field. So this perpendicular cascade generates finer and finer scale structure along the magnetic field, just as in Tokyo. So one thing we'd like to know is what is this relative anisotropy? And we can measure that in the solar wind relatively easily. And I'll come back to that in a moment, but let me tell you why it matters. And it matters because it changes the topological structure of the magnetic field. So this is a box with some magnetic field lines on it, on which I've put a whole set of essentially Alfvénic fluctuations with wave vectors just parallel to the magnetic field direction. And so if I identify a few of those magnetic field lines, you can see that basically they all wiggle in lockstep because the perpendicular correlation length is infinite. And so magnetic field lines that start one side of the box close together end up close together at the other side of the box. On the other hand, if I put in some wave vectors which are parallel but also some perpendicular to the field, so in other words, I have more wave vector anisotropy in that sense, you can see there are field lines that start close together that end up far apart. So this has important consequences for field perpendicular transport. Yeah? So for example, in the solar system, if you're interested in galactic cosmic ray transport, then two cosmic rays that start close together here, one's going to end up over here, and the other one's going to end up over there. So this matters. And the trouble is that as a spacecraft flies through this box of turbulence, these two cases are completely indistinguishable from a single cut. So the question then is, how do you actually go about trying to disentangle this, to try and work out which of these is closer to the truth? And one way that was discovered or realized essentially in the 80s by a group in Bartol is that you can take lots of cuts through this, taking advantage of the fact that the magnetic field direction varies. And if I travel along a magnetic field line here, then I'm going to see all of these wiggles. Whereas if I travel across the magnetic field line here, I'm going to see no wiggles at all because the correlation length is infinite in that direction. And vice versa if the wave vectors are perpendicular to the field. So if I have a wave vector parallel to the field, I've got a big slab wave like this. Then if I travel along this direction, I'm going to see the peaks and troughs. Whereas if I travel across it, I'm not going to see anything. It's an infinite plane wave. There's no variation in that direction. So by looking at how the power varies with the direction that I cut relative to the local field direction, I can see what the anisotropy is like in the fluctuations in wave vector space. So that was first done by the Bartol group. Actually, let me skip over that. And these are some recent results, just published actually, done by Robert Wicks, he's over there. And this is doing a rather involved wavelet analysis, but essentially taking advantage of the changes in the magnetic field direction to look at, rather than just looking at the bulk power spectrum, to pull out two bits of the power spectrum. One is the case when the magnetic field is parallel to the flow. So in other words, we're looking at K-perp, and the other is when it's perpendicular. And let me talk you through what you can see here. First of all, at low frequencies here, this is this f to the minus 1 stuff that we saw before. That's fine. And then we roll over towards f to the minus 5/3. That's what we saw before. We know that. We're fine with this. This is done with the magnetic field. And to add to the fun, this is actually turned into ion gyro radii here. Okay, so an ion gyro radius is here. Okay, so this is all MHD. What's interesting here, though, is suddenly you have two traces rather than one. And the lower trace here is what happens when you're running parallel to the magnetic field direction. Okay, so this is the K parallel stuff. And what you can see is that this has a different spectral index to K-perp. And this is a steeper spectrum, and in fact this goes as f to the minus 2. And what's also, I think, very interesting is this point here where the turbulent cascade starts in some sense. These are actually isotropic. Okay? So the input condition is isotropic in K-space, and as the turbulent cascade develops in MHD, it becomes progressively more anisotropic. And the level of that anisotropy as we get down here towards the end of the MHD cascade is what, 4 or 5 or something. Not your 1,000 or whatever it is, but 4 or 5. Okay, so what does that mean? Well, that actually is consistent with Goldreich and Sridhar's critical balance. So this idea that you balance the time scale of the nonlinear decay with the alphanic decorrelation time. This is essentially similar data, but cast in a slightly different way. If I go back briefly, if I take a particular scale here deep in the inertial range, and I plot basically power, how the power varies as a function of the angle of the field to the flow. So this is 0 and 90. And also I basically plot the spectral index here, so between 5/3 and 2. And that's what's shown here. So the details don't matter here, but the ratio of this number here at 90 degrees to this number here at 0 degrees tells you the anisotropy, essentially the eddy anisotropy. And so that number is something like 4. And this tells you the spectral index anisotropy between 5/3 here, perpendicular to the field, and -2 parallel to the field. And that's exactly what you expect for critical balance. So that's certainly not a proof of critical balance, but it's entirely consistent with critical balance. And again, this is for the magnetic field in the MHD inertial range. A prediction of Bolderev's 2005 theory is that there should be dynamic alignment. So this is the idea that the angle between fluctuations in the magnetic field and the velocity actually reduce as you go down the cascade. So delta B and delta V gradually become aligned with each other. John Podesta has published evidence for this in the solar wind. So this plot is complex. This is this angle, the dynamic alignment angle, the angle between delta B and delta V, And as you go down the cascade, helpfully this is the wrong way, so that's down the cascade, this angle drops. So this is touted as evidence of the existence of dynamic alignment in the solar wind. I would say, to be most charitable, that the jury is still out on this point.
It's not dropping monotonically, right? It has a minimum.
Yeah. Yeah. And actually, if you look at these scales, I don't know, if you think back to the plots before, this is the scale on which I didn't say it was the inertial range.
They're very large error bars.
Yeah, these errors are actually, I think you would argue as excessively pessimistic. The errors actually aren't anything like that big. Well, we can come back to this if you like, but
We do the statistical error on data that's much smaller than that.
yeah.
The large error bars come from systematic error, which Odessa has tried to estimate due to the solar wind velocity
Uncertainties.
uncertainty.
Yeah. Yeah. So yeah, I think this is excessively pessimistic.
I mean, these represent the certainty of the person who's producing the graph about the result.
Yes, that's a fair description.
I'm being very-
It's very nearly flat if you take in these
I'm
errors.
very pessimistic. I'd say it represents the fact that no one understands the curl up at the shortest timescales, and therefore to ignore it
So it's the size of theoretical uncertainty.
Okay, look, he's not here. Let's not. All right, let's press on. Okay,
It's listening.
that's it. Absolutely. Hey, I've talked about shooting school children. Everything else is relevant now. Actually. I thought it was bad when you said a rude word. I did something worse. So. Okay, so all right. So let's. I'm now going to talk about the transition through to iron scales. Okay, let me come back to here briefly. So I was talking about this anisotropy. Okay, the relative power anisotropy here tells you something about the anisotropy of the eddies. Okay, and I said that number was kind of 4 or something. If you look at, you can plot this ratio as a function of frequency and see how it increases, and it should in fact go up as f to the third here, because of the way that -2 and 5/3 are related. That's fine. John Podesta's actually plotted that. That's this thing here on the left-hand side. So this is the ratio of these 2 powers, okay? So they gradually split, and here's this kind of anisotropy about 4 or so. As you get towards the iron gyroscale, this goes up and up and up and up. This is actually not a third, but I would argue with an errors this is probably consistent with a third. You can see you then get rather complicated behavior as you go into what John is calling the dissipation range, and I'm agnostically calling the iron kinetic range. So there's a complicated structure here. What does it all mean? We think we understand what some of it means, but we certainly don't understand what all of it means. This is a graph from a paper by Chris Chen, who is there. There you go. Which tries to explain some of this by looking at how the anisotropy would vary as you go through the iron gyroscale and towards the electron gyroscale if you believed there was a kinetic Alfvén wave cascade between the iron and the electron scales that was also critically balanced. And so you predict this 1/3 gradient, which is the MHD critical balance, and then you predict a range of regimes which are very, very close together in frequency space, which have a range of scalings, 10/3, 8/3, and then we don't even know as you get into the electron scales talk. So
So 8/3 scaling goes from 1 to 2.
it's tiny, absolutely tiny. And I think you could argue quite happily that this was observationally unachievable. The widths of these regimes are related to the level of anisotropy to some extent. So if you had a less anisotropic cascade, if that makes sense, by the time you got to the bottom, these could be wider. And of course, they're also assuming that there's a critically balanced kinetic Alfvén wave cascade. If that were different, then these ranges would be different and so on. It's actually quite a subtle calculation. However, this 10/3 is about this kind of number here, the gradient of this bit here. So you might argue that this was some evidence for a kinetic Alfvén wave cascade. I wouldn't go so far. But in particular, there's this dip here. And that dip there is not anything you would expect from just transitioning straight from MHD into something kinetic like that. So that tells you something is happening around about the iron gyroscale. So the question then is, what is going on these iron kinetic scales? There are many things that might be going on, whistlers, kinetic Alfvén waves, what have you. We know that as you go from MHD scales to iron kinetic scales, there's a rollover here and there's a steeper spectrum. This has been known for a while. This is some recent data which is actually good quality. and you can see a relatively extended regime here, and this is the electron scale down here. And I'm not going to talk at all about down here. Milan will talk about what happens down there. That's a job, anyway. Okay. So there's certainly evidence for another power law, but what's actually happening down here? Okay, so if we look at the spectral index of it, you can see from this plot it's steeper. But in fact, it seems to be much more variable as well. These are histograms, again, of this spectral index scaling. This is in the inertial range. This peaks around about 5/3 here. But if you look in the dissipation range, it's extremely broad. Seems to be very variable. So more things are afoot than would be simply in the MHD regime. And that's I think, an important bit of evidence. Stuart Bale down here published this paper looking at the electric versus magnetic spectra as you go through the MHD regime into the ion kinetic regime. And you can see this is the electric spectrum, which then enhances above what you would just expect from V cross B, which is interpreted perhaps as evidence of kinetic alpha waves. I'm hoping, Stuart, are you going to talk about more about that later on in the week?
Just what I think it's not right.
All right, great. Okay, I'm conscious of the time, so it's a good job I didn't say more about it.
Not the data, but the interpretation.
All right, fine. I'm conscious of the time, so let me press on. I'm just going to talk very briefly about the latest work that we've been doing to try and understand this ion kinetic regime. So this is work done again by Chris Chen. This is looking in this regime here, and now this is using these 4 cluster spacecraft together. And the great thing about combining the 4 spacecraft is, I said earlier, if you've got a single spacecraft, you can only look in one direction as the flow goes past. If you have 2 spacecraft, by comparing between them, you can look across the flow. And if you have 4 spacecraft, you have multiple directions you can look relative to the flow directions. You have this little tetrahedron which whizzes through the plasma. And by comparing between them, you can build up a 3-dimensional picture of what's happening. That's what Chris has done. And he's ended up with estimates. This is actually power, essentially, is the color, parallel and perpendicular to the magnetic field. This is in kilometers. Okay? So remember, the gyroscale is kind of down here somewhere. So you can see that there's generally speaking, the power goes up as you go further away from the origin. But you can see the isocontours here are not circles. That's this idea that there are elliptical eddies here. It's anisotropy. But he can do something much more complicated. He can go and look at actually the structure functions as a function of scale for perpendicular to the field fluctuations and parallel as a range of directions relative to the local magnetic field direction. Okay? That starts hurting your brain. Don't worry. The point is they're roughly power laws, and let me explain a little bit more about what they mean. Coming back to the same kind of plot that I showed you before, this is power anisotropy. So if you look at the difference between that number and this number, that tells you roughly the anisotropy level. This is in the ion kinetic cascade. And that anisotropy level is something like 5. This is for the field perpendicular fluctuations. What perhaps is even more interesting is the spectral index scaling here. 7/3 is the prediction for kinetic alpha waves perpendicular to the field. This is not 7/3, but it's not so far off given how difficult this measurement is. But if it were critically balanced, the prediction for 0 degrees here for the parallel one would be 5. And this certainly doesn't go down to 5. But the problem that we have is it turns out, as we discovered quite late on in the analysis, that in fact a 2-point structure function, which is what this is, cannot measure a spectral index steeper than -3. So in fact, this may go steeper, we just don't know. It hits the bottom at 3. So this is not a proof of kinetic alpha waves, but it is consistent as far as we can judge. What perhaps is interesting is the field. Sorry? It's proof of anisotropy, both wave vector anisotropy and spectral index anisotropy. Absolutely.
Does it in fact indicate there's more power than we expect?
No, the absolute power level, there's nothing. Well, I'll come back to that very briefly in a minute, but there's really no. You come down the MHD regime, you go into the ion kinetic regime, but nobody really knows how you transition over the boundary from one to another. Yeah. So I don't think there's really a statement about how you would. Yeah, the relative anisotropy. Yeah. But the red point.
There's a critical question there, which is how much energy
Yeah.
is thermalized at that. That's right.
Yes, and I'll come back to that very briefly in a moment, because I'm conscious that I'm over. Okay, this is delta B parallel. So this is the field parallel fluctuations, and as I understand it, these should be scaling the same way as the field perpendicular fluctuations for kinetic alpha waves. And in particular, the spectral index scaling is completely different. This scales as -2, and it's not really that anisotropic. So that's a hint that kinetic alpha waves are by no means the entire story although they may be part of the story. Talk to Chris if you want to know more. The other thing is density also scales anisotropically. This is a recent, very interesting paper. This is the spectral index of the density fluctuations as a function of this angle in the ion kinetic regime. And that is anisotropic too, and actually that looks freakily like the MHD prediction scaling. So that goes from 5/3 to -2-ish, although it's a bit hairy. So I don't think anyone understands those data. They're very interesting, and that's very much a work in progress, I think. Finally, what I want to talk about is kinetic instabilities. Justin Casper kind of kicked this business off with various other people as well, and Lorenzo Martini, who's here, has been involved with this kind of stuff. But this is actually a plot from Stewart's paper. This is a phase space of perpendicular to parallel temperature anisotropy to parallel plasma beta, ion beta. Okay, don't worry about the details. There are two dotted lines, well, there are three, but two of note. One dotted line here says fire hose, the one at the top says mirror. They're the instability lines for those two instabilities. And you can see the data tend to sit this side of it, and the color here, this is from years and years and years of solar wind data, by the way. The color here is the amplitude of the little fluctuations in the magnetic field on kinetic scales. And you can see they tend to be higher around the instabilities. And we believe, what Lorenzo showed, is that the solar wind expansion basically drives this distribution this way, where they then end up at the fire hose and mirror instability points, or some of the time they do. And then you can see from this plot that they are generating fluctuations. So suddenly this raises the question, how much of the fluctuations that you see at the ion kinetic scale have not come down the cascade at all? How much of them have just appeared like magic from nowhere, from the instabilities? And finally, this is coming back to Robert's work earlier. I just want to show you some evidence that we think we have for the fire hose instability. So this is the plot I showed you earlier. Just to make it slightly easy to understand, I'm going to now flatten this one by 5/3 to make it flat, and this one by 2 to make it flat. Okay, compensator spectra. Pop. This is the perpendicular one. This is the gyroscale. It rolls over just before the gyroscale. That's fine. What's interesting is the parallel one, which is -2, and then there's a bump. And that bump is entirely consistent with Lorenzo's simulations and other ideas about this being due to the fire hose instability here. So this, I think, is good evidence for an enhancement here for the fire hose instability, at least some of the time in the solar wind. I don't think it's proof, but it's interesting evidence. And that, we think, probably explains the little bit in John Podesta's plot as well. So this idea about you have a level of anisotropy you generate through the MHD cascade, you go through the gyroscale into the next ion kinetic regime, the next cascade, but the amount of anisotropy doesn't just roll across. There's kinetic processes that happen there too, and they may be adding anisotropy, they might be removing anisotropy, and they might be adding power or they might be removing power. Okay, the other thing is, forget it, I'll finish. Actually, can I, this is actually kind of a question, almost kind of related to what, I put this in after your talk.
You can pretend it's a question.
I can pretend it's a question, that's right. So, one of the things in the solar wind is there's an awful lot of structure. You know, I said right at the beginning, you've got to remember the context, the structure, and there's actually structure everywhere. And there are discontinuities, there's sharp changes in the magnetic field. Do they come from the turbulence, or do they actually come from structure from the sun? We don't know the answer to that. There's a very interesting piece of evidence from Jovian energetic electrons, okay? These are relativistic electrons that come from Jupiter's magnetosphere. They're inside Jupiter's magnetosphere, and they get out, okay, into the solar wind. These electrons are essentially going pretty well at the speed of light, but their gyro radius is sufficiently small that they're actually very tied to magnetic field lines. Unlike ions, they don't scatter very much off field lines. So you can think of Jupiter, and Jupiter's magnetosphere is big. So if you look at Jupiter when it's up out and about in the sky, its magnetosphere subtends a larger angle than the moon does. So it's actually very, very big. Anyway, but it's vaguely a point source. So there are magnetic field lines that intersect with Jupiter's magnetosphere, and these Jovian electrons get out and they race along those magnetic field lines. And we can detect those electrons all across the solar system. We're at 1 astronomical unit from the sun. Jupiter is about 5. We can detect these at the Earth, and we can actually detect them very coherently at maybe 2 astronomical units from the planet. Okay, they get quite a long way. They don't scatter along the way. Here, this is 2 days of data. And this essentially, just take this one. This is counts of these Jovian electrons. You see they spike up and then they go away again. And they spike up and they go away again. And these are very, very short boundaries. Okay? So this is something you're a few hundred million kilometers away at this point, and this boundary is maybe a few minutes long. So these are telling you about fine-scale braiding structure in the magnetic field. You know, I showed you those little pictures earlier, like these things about, imagine there's Jupiter, right? And it lights, think of Jupiter as like a flashlight, and the magnetic field lines like fiber optic cables, right? So you just light a set of fiber optic cables. Anywhere you are in the solar system at that point, if you're a spacecraft, you can measure them, or within a couple of astronomical units. Suddenly, you're cruising along, you pass over a magnetic field line, suddenly you see Jovian electrons and then they go away again. That tells you at that moment in time you are magnetically connected to the planet. So these Jovian electrons are telling you about this field line braiding over very, very large scale. And as you can see, it's incredibly fine, and it's actually incredibly structured. So very little work has been done on this in a statistical sense, I think, to tease this out. But I think this is a data set that's actually potentially very productive in trying to understand something about field line braiding, and I think field perpendicular transport, which may actually be relevant to tokamaks as well. Okay, so I will finish. I'm sorry I'm late, Alex. What we know, there are anisotropic cascades on both MHD and ion kinetic scales. That's certainly true. There's anisotropy in a range of things that we measure, but there are some interesting differences between the different parameters that we measure. There's certainly evidence for kinetic instabilities, at least some of the time, and we know that imbalance between the two alphanic modes is also present at least some of the time. But I think still the question, is there critical balance on either MHD or ion kinetic scales, is unanswered. I think probably yes, but there's no conclusive evidence for it. What is actually going on the ion kinetic cascade? I don't think anyone actually knows yet. What is the effect of imbalance? I think we're only just beginning to think about that seriously enough. And how important are these instabilities for putting power in, and these structures as well in affecting the dynamics? Okay, so I'll stop there. Thank you.
Tim, you had the example of the Jovian electrons. There's another one that's really cool. You see ions coming from a small flare at the sun. They're a little dispersed in the time they get to you, depending on their energy. And from that dispersion curve, you can see there was this little puff of ions at a lot of different energies. And what can happen is you'll see this, and then suddenly they'll disappear for a few seconds, and then they come back again, and they disappear again. So it's telling you you're walking back and forth, being connected to that one point on the sun. It gets to a theme in the solar wind, which is things tend to be either a lot easier to happen than we think they should be, or a lot harder to happen. And there are examples with flares where the perpendicular transport across the field seems to be as efficient as parallel transport, a big question in our field. So you showed those examples of slab versus 2D, and how in the solar wind we think there's definitely it's easy for field to diffuse perpendicular to the field. Now I'm wondering, in the spirit of this meeting, you were talking about your flux rope simulations, and well, it's sufficient for me to have this periodic flux rope winding around my tokamak because it's not meandering very quickly. And for us, I don't think we could necessarily say we could do that over a large scale. If I move just a little bit in the solar wind along the field line, I'm no longer looking at, near adjacent field lines do not necessarily stay adjacent for a very long period of time.
Yes, that's a more blunt way of saying what I was kind of gently trying to say, which is, I think that's right. I think that the lesson from the solar wind is you only need tiny amounts of that perpendicular variation in the field to actually end up with quite large field perpendicular transport on a large scale.
That could be
Much
very
more than you
interesting
would
to
expect.
Remember that an important difference is that in the tokamak you're setting up a very, very strong mean field with small perturbations on top of it, while the solar wind LPV at the large scale is one. Right? So it's if you go to very small scales, that's not very important because the fluctuation is still very small.
But as Justin says about these,
But
certainly the solar energetic, the flare event cases, actually, you're crossing across boundaries where sometimes you can see nothing at all. Yeah, there's no variation in the field at all. So the mixing has happened somewhere else as well. So I think there are things we could do. There's a crossover there that we can.
So one of the things there is to look at the confinement of electrons versus the confinement of ions, particularly the confinement of very energetic electrons. In cases where we have deliberately or for other reasons made a set of very energetic electrons, you can look at how well they're confined, because they tend to follow the stochastic field. And there was a lot of work in the 80s looking at the comparison of confinement of energetic electrons.
Even earlier than that, Steve. Even earlier than that.
Just before Noah. Yeah, and this is the probe. What's interesting about a lot of fusion devices is that ion and electron confinement is very similar. Not you know, to a factor of 2, but if you had very stochastic fields, you might imagine that electron confinement is the square root of the mass ratio worse than ion confinement, but it's not.
So that does imply that the transport is therefore field line wandering rather than diffusion across field lines. Yeah? If they're doing the same thing, then that implies that the field lines are just moving them somewhere else, does it not?
No, not
No, 'cause they
necessarily.
go faster
Just,
along the
see,
field
because E cross B motion is the same for an ion and an electron. The only thing is that electrons move along the field line much faster. And what probably happened, I don't actually, probably not exactly right, but one of the things that happens is that the electrons that do most of the transport are trapped ones. They're the ones that are bouncing. They can't average over the structure by moving parallel to the field.
I mean, you see this in solar flare observations where the foot points, you have a flare, and the Bremsstrahlung foot points, which indicate the electron foot points, are different from the gamma ray line foot points, the proton. So there's clearly something. In principle, the acceleration all happens near the loop top, but you see that they land in different places.
Great. So this Jovian flashlight is interesting. Are you sure it's steady state?
No.
Are there reconnection events that are in?
Yeah, that's right. The escape mechanism is not entirely clear. I think it probably is reconnection related. Yeah, no, it's not entirely steady state, but it's not as variable as that. So we do have Ulysses did it, and Galileo has some data too. We do have flybys of Jupiter where actually the average rate goes up and up and up as you go towards the planet, and so you can see what it's like close by as well. And no, it's not as variable as that.
And what is it that generates these relativistic electrons?
I don't know. They're inside the magnetosphere, so they're probably
The Jovian electrons?
Yeah.
Well, I think it's just fast Fermi, isn't it?
Oh, okay.
I think it's fast Fermi acceleration.
Yeah,
shock.
okay. Oh, is that right?
Yeah, I believe it's foreshocking.
I thought it was magnetosphere. Okay. Yeah.
You discussed the dissipation range in a small kinetic scale, but the spectrum still looks following the power law. So is there any observation of the dissipation spectrum with the exponential decay, which is usually observed in the dissipation range of the free tubing?
No, I think it's pretty... Okay, I should explain this plot. I went over it quite quickly. Ignore these little bits up here, okay, because they're instrumental. But the spectrum here, I think, is pretty clearly power law in the ion kinetic regime. So the ion gyro radius is here, the electron gyro radius is here. There have been some statements that below the electron gyro radius it might be exponential. But I don't think anyone really knows at this point. But over this range, it seems pretty clear it's a power law.
But unless we observe the exponential decaying spectrum, the cascading process is expected to continue.
Yeah, so if you
Yeah.
look at where
Ion
the
and
dissipation is there,
Right.
at around k rho I, I mean, theoretically, you get ion Landau damping at about k rho I, which is about 1 in there, frequency of 1 hertz. That's, so the Alfvén wave, in its business of converting into the kinetic Alfvén wave, you get some ion Landau damping.
Okay.
Because beta is about 1, so the Alfvén speed and the thermal velocity of the ions is about the same. But as you go further up down there, the phase velocity of the kinetic Alfvén wave gets too fast for the ions. And therefore you go into a region of no dissipation down until you get closer to the electron scale, at which point the phase velocity becomes comparable with the electrons, and you get electron number. So actually you get bands of, theoretically you should get bands of dissipation. Ions at about 1, and the electrons at about, 60.
Yeah. It depends how much you're willing to take from a plot like this. I mean, if you look at it and squint at it, you might argue that there's a flat bit here, straight bit here, but actually it bends up before it bends down. So you could say, well, actually maybe there's a bit pulled out here. But it's very hard to tell from these kind of plots. You're pushing the observations very hard if you're trying to take that kind of level from it. I think it's very difficult to do.
Can I just point out to those of you who are still around next week, there will be a seminar by Greg House who will show gyrokinetic simulations of this range, where he is obtaining a power law cascade between the ion and electron scales. Let's see. Greg wanted to comment again.
Where is the ion cyclotron frequency on this scale?
It's of the order of a few seconds, I think. Oh, is it? Oh, good. Yeah.
That's the ion cyclotron frequency?
Yeah.
But that's not.
But it's not desperately relevant because it's remember the frequency here is not, you're not sitting there and watching the plasma like this, the stuff's going over. So every frequency is actually a spatial scale. So the relevant frequency is the gyro scale.
Which has been a source of confusion in our field.
Oh, absolutely. Oh,
So I guess that we have to Doppler shift this.
well, this comes back to this Taylor hypothesis issue. So if you believe you can do all of this, it's just done in spacecraft frequency, and these things are basically put on the assumption that Taylor's hypothesis is valid on this scale. It's almost undoubtedly valid here. Is it valid there? I agree.
So if I were to draw a conclusion from your earlier work, you showed that the K parallel and K perp spectrum differ by K to the 1/3 only.
Yeah.
And if you extrapolate to K perp rho I of 1, K parallel rho I was only a fifth there.
Yeah.
And so frequencies, our expansion parameter in tokamaks for ITER might be 10 to the -3, but here it's only 1/5.
Yeah,
So
yeah, that's right.
The cyclotron frequency is only 5 times shorter, 5 times faster than the scales.
But it's not clear that if a kinetic alpha wave cascade transitions through the ion cycle frequency, will actually do much to it. That's unknown. I mean, this is a subject of active research, I think. But it's somewhere in the dissipation range. Lorenzo, I think.
Just about the previous question, because there are some observation of the non-power law behavior at the electron scale.
At the electron scale, that's right. Yeah, that's right. But for the
I've seen some kind of dissipation there from Olga Alexandrova.
that's right. Although I think that's I would say that observation or that interpretation of the data might or might not be right. I think it's a bit iffy as to. I don't think there's conclusive proof. It's exponential.
It's difficult to say if it's exponential, but it seems to deviate and to depart from a single power law.
Okay.
Well, of
Which
course,
could be
beyond the electron scale, you should be damping things.
Yeah.
Right? There isn't really, at low frequencies, certainly below the electron scale, there isn't much going on.
You're running out of options, aren't you?
You're running out of options, exactly. Yeah.
But one thing I thought was, I'm kind of going to ask you a question. Can I ask you a question?
Yeah.
So
The speaker has a question.
we've got kind of 2 orders of magnitude here, roughly, between the outer scale, between isotropy and the gyro scale. And we've ended up with an anisotropy at the end of 5 or 6 or maybe 10 if you're lucky or whatever. But you're talking about the anisotropy at the ion gyro scale is of the order of 1,000 or so. Is that the kind of number you were talking about?
Yeah, it probably isn't as much as that, between 100.
But remember, delta B over B in the top chart is 10 to the minus 4 or 10 to the minus 3 or something like that, right? And delta N over N is what? 10 to the minus 2 or something like that.
And as you said,
While here it's at the ion scale, right? But here it's what's delta B over B at
it's
the ion
a
scale?
few percent. Small. That's very small actually. That's it's one there, but it's really small. And so your comment earlier was about critical balance here, yeah? So the question is, what is the scaling amount here, parallel and perpendicular?
The thing is, in a tokamak, the instability will be stark. Right? The instabilities themselves are completely anisotropic.
Yeah.
So you're injecting energy anisotropic.
Anisotropic way, yes.
Anisotropically. But you're injecting energy, or it seems that solar wind is having energy injected anisotropically.
Yeah.
And it's developing in centers.
I think that's right. This was a very surprising graph to me when I saw it.
At the outer scale, that's true.
That's right. Here, I'm astonished that this is isotropic here. Maybe I shouldn't be, but I was really surprised to see this.
Well, also, if you have injection by 5 right, the 5 likes to be oblique. So it likes having K parallel of order of K perp. So the 5 injection, it's not exactly isotropic, but it's certainly not K parallel, much less. Well, you see, that's why you have a blip in in that spectrum because it's injecting. It likes having K parallels that are actually over the K perps.
Of course, you could have a comparable bit there that you wouldn't see because this power. If you put that much power in there, you wouldn't see it because this is a logarithmic scale.
But the growth curves of the fire hose instability, as observed in the solar wind, are much more consistent than a parallel node. So there are a lot of ways to see that it's
But
anisotropic.
even if it was completely parallel, that would still produce a blip like
Yes.
this, right?
Yeah.
The point is that the fire hose likes K parallel.
I may be misrepresenting this. What's the sound right here? What's your best bet? Maybe between Robert and Lorenzo, they might want to comment on.
Well, I would say you can't say whether it's parallel or oblique from that because you can't see the perpendicular energy injection because it's too low. But the frequency or the scale at which the power injection happens is very, very good match.
This will be discussed in detail on Wednesday.
Yeah.
Yeah, I'll show some alpine ratio measurements near the fire hose threshold, which
Okay.
So Wednesday morning will be devoted to undermining gyrokinetic.
What?
Right. Anyone else wants to ask anything else? No? Okay. Then we come back at 2 o'clock. Lunch, books, and course. You can figure out that thing.